Let's go.
So we can go ahead. Are you recording?
No.
So we have like, so basically the cache will be storing items key value pairs, right? And now the idea is that if the key exists, we want to return the value. So for example, we want to do a get function. We want to get one, right? We pass the key and one is here. So it's going to basically like return to us with one, right? Now the next thing is, let's say we want to update the value, or we want to like, yes, update a value or even add a new value, right? But then remember, anytime we instantiate an object of the LRU cache class, we would have, it will come with a capacity, right? And let's say for this, our capacity is like, this question in particular, the capacity was two. But let's say for this one, our capacity is three, right? And now we want to add or like put a new um a new value or a new item into the hash map, right? And put those with key and then value. So let's say at this key four, we want to put a value of six, right? Now remember that the item we just got was one, right? Let's say when we're updating an item, this is the order right now. And since one is what we just recently like used, we would want to find a way to move one to the front, right? So that now our least recently used item is this. Does that make sense? So when we try to put four here, what it's going to essentially do is that it's going to update our cache with four mapped to six. But since now our length of the cache is four and is greater than the capacity, which is three, we would want to evict. So that is where the eviction policy comes. Like the caching has an eviction policy. So, and I think even in normal cache system design caches, they have something like time to live or whatever. I don't know if it's the same, but with the eviction policy, it means that okay, now the length or the capacity of the cache is three, and then now we have four. So that means we want to remove the one that we haven't used the most, which is the least recently used. So that means we will remove this, right? You follow? So like right now, if we want to try and get two, it should return negative one, because over here it says return the value of the key if the key exists. Otherwise, return negative one. So if we do something like a get of two, which we just evicted, it will return to us negative one, right? So that's basically like the entire idea of this question. We are just trying to design a cache that can effectively get and then update, right, based off a certain rule or based off some rules. Now, here's the catch. We aren't obviously going to use just the catch. Someone else needs to come up. We aren't obviously just going to use a cache to um, to solve this, because mind you, hash maps or yes, hash maps don't store things in order, right? So you may want to like use a list, right? So essentially what that means is that whenever you try to update the cache, let's say for example you try to add one to the cache, when you add it to the hash map, you also add it to the list, right? Then let's say the next thing you did was you added two. You add to the hash map, you add to the list. Then the next thing you did was added three. Now the next thing you want to do is add. Hey, the screen has stopped sharing again. Oh, the problem is me.
Check your laptop. Oh. Okay, it's back.
So, like I was saying that you can't use the hash map to store the order, right? So you want to make use of another like data structure, which is a list, right? So let's say we are not even going to make use of the linked list. But the thing with the list is that imagine anytime we add, let's say, so for example, right? um we haven't added four. We have one, two, three. So let's go back to our old example. One mapping to one, two mapping to two, and then three mapping to three, right? So now this is what we have in our hash map and then also in our list. And then remember the capacity for our cache is 2. Now, we try to get one, right? And I said anytime you perform any operation on anything in like the any item in the cache, right, you would want to make it the most recent use, right? And that way, what we mean by that is that we would want to like bring it to the, let's say, the end of the lists. Here's why: because whenever you want to should I say, pop it from there. You want to like append to the list is done at the end, is done in constant time. So let me even just explain so it will be clear. So right now we want to try and get to one, right? So we try to get one, we remove one from here, and then we add it to the end of the list, right? Now you see that with lists, whenever you remove an item, you shift it back because this thing that we just removed means that now there's a space here in memory, right? So to reorder the list, we have to move all the items, which means that removing something from the list would make it go up n time. So imagine you have a list or a cache with a capacity of like 100 or infinity. That means that it's going to be very, very slow because if we remove at the beginning or at index 0, we have to shift all the other items to the front, right? So that is where the linked list comes into play. Because with the linked list, what essentially we will be doing is that we would have a, let's say, a dummy node called head and another one called tail, right? And they are doubly linked list, so they'll be connected to each other in this way, right? So obviously they'll have a next pointer and a previous pointer, so they'll be connected to each other in this way. So when I add, right, when I add to the head dot next is what gives you the least recently used, right? So that means that whenever you add two close to the tail, right? So for example, let's say I add one, I'll add it here. Then I'll add two. Then let's say I add three, right? So let's say I add three, and then I think we also be pointing to here. Like I said, they are doubly linked, list, so they are connected in two directions, not just one direction. Um, so this way, right? Now I want to get one, right? Since you have a function that would, let's say, essentially remove this one from here and connect it here so that one becomes the most recently used and then two becomes the least recently used. And because it's a doubly linked list, we can easily access like this one over here by just doing something like self dot head dot next. And that way, like you realize that with linked lists, we are not shifting anything in memory. Remember, like linked lists are connected with pointers. So it's just about removing the pointer and then reconnecting it, which means that in essence, removing is not constant time. So it's not linear time, but it is constant time. I don't know if what I'm saying makes sense. Because with the list, if we are removing from the index 0, we would have to shift all the items. And that would mean that like removing in essence is like linear time. But with the double linked list, anytime you remove from here, right? Let's say remove x from one from here. So this one comes here, and then we'll bring it here. Okay, this way, right? That means that you just need to reorder the positions of the pointer. So this H would now be connected to two. So if you want to essentially like get least recently used, you can just get it using the pointer even. And also like we are rearranging it to doesn't mean that you now have to shift the items in the linked list. So let me see if I can even draw something with
Ish, ish, ish.
oh, I'm sure this is what we did the last time. Okay, so let's say for example we have something like this, right? How is it looking this way? Let me go for it. We have something like um this, and this is like a space in the memory, right? So with the arrays in memory, if we have something like 0, 1, 2, 3, 4, right? Immediately we try to remove 0. What that means is that now we now have to move. So arrays are like contiguous in memory, contiguous blocks of space in memory. So we have to move. Because if you want to store something in an array, and you want to store it in memory, and let's say your array is of size 5, right? The computer has to find a place in memory that is contiguous, that can store all of these items in a certain kind of order. But with linked list, you can have like a memory like this, right? Where, for example, 0 can be here, right? And then 1 can be here, 2 can be here, and then let's say 3 can even be here. But the only way they are connected is through pointers, right? So I'm drawing this, but like this is not how it is actually. It's just to visualize. Then this is also probably connected to this, right? Then this is also connected to this. So you realize that they are not like they are not contiguous. Does that make sense? So that's exactly what I'm trying to say over here. That with this, once we remove, we don't shift anything in memory. We just reorder the pointer, and that's what makes it more efficient as compared to using the list and then the hash. So yeah, does anyone have any question before like we attempt to do that? Like, any question?
Now you can proceed. I think I'm following.
Okay. So I guess now it's time to put the code in the back. So anytime we instantiate an object of the class or the LRU cache class, we would want it to come with a capacity, right? So all of the time we would have like a capacity. And here we are just going to say that okay, that capacity is equal to the capacity. Also, we wanted to have a hash map. This is what's going to help us to like the hash map will be storing items the in the form of keys mapped onto nodes, right? And these nodes would have a key and a value. Now we realize that we don't have the node class, so we have to create our own node class. So we have like a class node, and then I think we need to instantiate like the init of the node. So that means that anytime we have a node or we call the node class, we would want to pass a key and a value, right? Um, so our self dot key will be equal to key, and then our self dot val equals val. Now we will have like our remember it's a doubly linked list, right? So doubly linked list mostly have like a next pointer, which will be none in this case, and then a previous pointer, which will also be none in this case, right? Like
Um,
anytime we instantiate.
yeah,
Yeah.
just quickly, what are we using the key and value for exactly?
What are we using the key
The-
and value?
yeah, because I, when we talk about double linked list, you are in most case you are concerned about the pointers and the value of the node itself. So I'm a bit confused about why we are adding a key to it.
You mean for the node?
Yeah, for the node, yes.
So they are thinking it should just be the value.
Yeah, maybe there's a reason for it. So that's what I'm trying to find.
Yeah, I think I will get into it when I'm doing like the
Okay.
yeah. So for here, like we would also want to have I think a head, right? And anytime you call the head, it's going to be just a dummy node, so you can just make it self. And then I think for the tail too, it's going to be self dot tail, which is also going to be right. But you do realize that these two are not connected, so you have to connect it yourself, right? What I mean by that is we just have like a head node and then a tail node. But what we want it to be is like we want it to look okay, like connected to each other, right? Both pointing to it. And here's how you do that. So you do like cell dot head dot next. So the next pointer will be pointing to cell dot tail. And then I think you also have like self dot tail dot pre. Like so that's like the previous pointer. So what I mean by that is let's say um we have a head and then we have a tail, right? Um so we are connecting the previous to the head and then we are connecting the next from the head to the tail. Does that make sense?
Mm-hmm.
So self dot pre is going to be equal to self dot right. Yeah, I think this should be it for our LRU hash.
For your line 14, I think there's a you made a comma for a dot for instead of a comma for the.
Yes. Okay. So now we want to try and get right. Now we'll go back to what they're asking us to do. Return the value of the key if the key exists. Otherwise return negative one. Right. So if the key is in self cache. So here's why we are even doing still keeping the cache. We're keeping the cache because we want to like look up in constant time, right? So we
Okay,
can
okay,
quickly
okay, 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 okay.
so you get
Yeah, I get it. I get it. I
if
get it.
the key is in there, like if it's in there. So remember, you okay, we're just going to do like return self dot cache, right? At the key, right? Let's return the value of the key that key exists. So it's just going to return to us the actual node and the node that is being returned to us essentially has like what's it called?
Value.
Yeah, the value, right? Okay. So um else we return negative one. But that's not it, right? That's not all because we said anytime we perform an action or a function on the cache, we want to remove it from the I don't think I think I cleared that. But we want to remove it from wherever it is to put it like the most recently used. So let me just try and like write comments to show what I mean. So for example, you have H and T, and these are your dummy nodes. Anytime you instantiate, you have like H and T, right? Now the first thing we did was we tried to put one, right? So we connected one here, right? Now we try to put two. So we have two here, right? Now the next thing we want to do, I'm playing this example, is we want to get one, right? When we try to get one, since it's also an action, we would want to remove one from here, right? And then like bring it to the front because now in this case one should be the most frequently used. One is the one that you just perform the function on, and two is the one that hasn't like had any function performed on it, so it's the least recently used. So essentially anytime you perform an action you want to remove it and then add it back to the linked list to make sure that it becomes the most frequently used, and then you have like your least frequently used close to the age.net, right? So essentially what we'll do is we'll have like a function. I'm yet to write that function. Self.remove self.cache the key, and then we add it back. That's going to be self.add self.add the key, right? Index add the key. Sorry, this should so we can have a function here called def let me see def remove, which is going to remove a node, right? So you can just pass a node here, and then just add this for now. We come back to this. Then um here to yeah. So these are two functions that we'll be making use of. So our next function is the put function, and essentially with the put function, we're saying update the value of the key if the key exists. Otherwise, add the key value pair to the cache. Sorry. If the number of the keys exceeds the capacity from this equation, evict the least frequently used key. Great. So we can check if key is in the cell that's cached, right? Um, what that means is that we are checking if the key is there. If the key is there, we would want to remove it, right? So we'll do like self dot remove self dot cache at the key, right? But then if the key is not there, we would want to do something else, which is create a new um like create a new self dot cache at the key will be equal to the node view value, right? And then you would also like add it to the W language, right? Self dot add self dot cache at the I would have done like an else condition, but then we realized that these two lines apply to both cases where the key should be in the cache and the key is not in the cache. So essentially, what this is doing is that if the key is in the cache, we want to remove it from the cache or from the no from the W link list, and then like update it right in the cache, and then like add it to the W link list. But if the key is not in the cache, this if block will not run, and it's just going to create a new node in the cache, and then also like add it to our W link list. Right now, don't forget we said if the number of keys exceeds the capacity from this location, evict the least frequently used key. So what that means is that if the length of cell dot oopsie, um, is greater than the capacity, we would want to remove the least frequently used, right?
I,
So we
I, I
can say,
think I think you made a mistake. Oh. You did if length of the brackets, the length
yeah,
of the
yeah, thank you. So remember we said our least recently used is going to be placed like the node at the next of the head, right? So we just quickly access that with cell.head from node, right? And then we will just do cell dot dot remove, right? LRU. And then obviously we would want to also remove it from the cache. So we'll delete self dot cache um at
Okay.
dot the key because we want to like use the key to delete it. I don't know if that makes sense. Because
Mm-hmm.
every node comes with a key and a value, and to delete, you get it. You just
Yeah.
need to access the key to the node. Yes, so that's it for the functions, but we have to come to the actual thing that is effectively removing and then adding, right? So remember I said anytime we are removing from from the W lane list, right? We are essentially going to, so let me just also have the node. So we'll have like an N node. So the N is for the node, H and T are like the head and tail, right? So now we want to remove this thing from there, right? So what that means is that essentially we want to try and like change the pointer, right? So we want to point head to tail, and we want to point tail to head. But the catch is that you may not have access to head, right? And you may not also have access to tail. The only thing you will probably have access to is the node. And here's why I'm saying that because imagine we have another node here called J that we want to remove, and then we are trying to use the pointers of H and then the pointer of T. It's going to be messy, right? So we would want to just make use of the pointers of the node that we are given or the node that we are trying to remove. So what I mean by that is we would first say that the node, so node, this thing trips me over the a lot of time. Hope I'm not the only one. But node dot previous, right? So what that means is that this H we have over here, its next pointer should be pointing to um
The, the current
node
nodes next.
dot next. That makes sense, right?
Mm-hmm.
I hope this is correct. Then so that means that this H we have here, so because this is node dot previous next should be pointing to this node's next because we're trying to just override it, right? Then now since we've done the previous, there's something else we need to do. And I said
The,
I feel
pre-
like I need to
the, the previous node of the current node.
come again. So now we've connected this all the way to J, right? Now we
Mm-hmm.
want to connect J back to H, right? So that means that node dot next dot div is going to be equal to, we are connecting this. This is going to be node dot div. That's it, right?
The previous. Oh,
You said because this is the node,
yeah, yeah.
this node we have here. Yeah, I think it's not correct to again, but then the add function. With the add function, that one too, we have like a head and then we have a tail, right? And anytime we are adding, we want to add close to the tail, right? So that one, we kind of have access to the tail, right? So let's say we want to add one to to the to the tail. So we'll say something like self self come on, keep going. Okay, so let's say we want to add one. I'm going to put node here, right? Guys, as you can see, I'm sweating here. Um, so we have a node, right? And we
Yeah.
want to add one to this, right? So we can just say like
Until or previous.
self dot tail dot previous, right? Dot next is going to be equal to the node, right?
Mm-hmm.
Then we would also want to connect the node back to it. So essentially, we're going to have something like um, node dot previous. I'm blank. I don't think it's node dot previous. So we want to connect this node, right, back to. We've already connected 12.tail.previous and next to the node, right? And now we want to connect the node back to this, right? And this actually is self.tail.previous. This is going to be self.tail.previous. Oops. Guys, I need help.
You
Okay.
can keep information about the temporal node you're supposed to point stuff to like a temp variable, as in there's a previous node between, yeah, between the last till
I'm going to
end. So
put the next loop
yeah,
where we are going to have like probably connect this to this, right?
yeah,
And connect right here,
yeah,
which means that node dot next will be equal to self dot tail, and then
yes,
self
or
dot
till
tail
previous,
previous, right, will
yeah,
be equal to the node,
yeah,
right? Now this self dot tail dot previous dot next is equal to the node.
yeah.
So that
So
means that this which we have over here is connected to the end. So that means that node dot previous would be connected to self dot tail dot previous. I think this would be interchanged. I am not sure. Yeah, I guess we can run it to see.
line 30, is it 42 has the cache spelling.
But
42.
I have a question, right? And for the add part, why don't they like use the head? Like, you get my question? Like, yeah, using the tail, which is fine, but if you use the head, wouldn't you just do like head dot next is equal to node, then just connect the node, like node dot next is equal to like the tail.